Hello and welcome to the Qubit Guy podcast, brought to you by Classiq, the quantum algorithm design company. My name is Yuval, and my guest today is Shantanu Ganguly, a systems architect from Cisco. Shantanu has a new book out about quantum machine learning. We talk about this book, Flying Qubits, the challenges in moving quantum machine learning to production, and much more. We hope you enjoyed this episode. Please let us know how we did by emailing hello@classiq.io. That's hello@classiq.io. Hello, Shantanu, and thanks for joining me today.
Thank you, Yuval, and thanks for having me. And most of all, thanks a lot for pronouncing my name correct. I'm really grateful.
My pleasure. So who are you and what do you do?
My name is Shantanu Ganguly. I currently work for Cisco Systems in UK. One of my duties at Cisco Systems today is to is being part of their steering committee for quantum tech internally, which is one of their internal projects. And I have a background in physics and math. I've always been passionate about anything that's science, especially quantum computing. So I work closely with UK government projects and some enterprise financial bodies in the UK. That's me.
So first, congratulations on the book. I think you have a new book out on quantum machine learning. Could you please tell me a little bit about that?
Thank you very much. Yes, it was a great opportunity offered to me to work on that. And initially, I thought it would be easy to do. It was not nearly as easy as I thought it would be. The subject matter is quantum machine learning, and the reason I chose that subject matter is because I'm very passionate about machine learning in classical sense, what it does, and I'm even more passionate about quantum computing. And I've always been passionate about quantum computing. I have a background in maths and physics. And last 5, 6, 7 odd years, as quantum computing became more and more relevant to industry, and organizations such as Google, IBM, etc., started to pump money into the technology, and it brought out relevant developments, I got really more and more excited. So the book is really about addressing basics of quantum machine learning, algorithms involved, and most importantly, addressing a gap that I thought existed in most quantum machine learning literature, so to speak. So for example, there are monumental volumes by Peter Vitek. I think he wrote the first book on quantum machine learning ever back in 2011. That was followed by Maria Schul and Petruccione's monumental volume on supervised learning in quantum machine learning, and that was a great book as well. However, and this has been followed by an explosion of different algorithms, different research in literature and research media. However, one of the things I always missed and struggled with myself initially when I started to look into this field is how do all these algorithms, all these theories, which are very new, very growing, very recent, translate into codes? So as I started to look into that, what became apparent is not every algorithm works efficiently on every quantum computing platform. There are, as we speak, there are several variants of quantum computing platforms today. D-Wave came out with the first commercially available quantum computer, and they use annealing. IBM came out with superconducting qubits, and they use a gate model. Rigetti came out with similar superconducting gate models. Xanadu and PsiQuantum are working on photonic quantum computers. And more I looked into these algorithms, going back a few years, more I looked into these algorithms, more it appeared to me that not every algorithm works efficiently on every platform. For example, right now today, there are studies that have been done which claim that certain NP hard problems, such as MaxCut, might work more efficiently on DUF systems computers using Kubo than on gate model computers using quantum approximate optimization algorithms, QAOA. So all these variations in and challenges when it comes to applying algorithms to platforms is what actually triggered my interest in writing the book. So hence, the book covers most major quantum computing libraries in existence today. It has Google Cirq, it addresses Rigetti, PyQuil, and Qvium. It addresses IBM's Qiskit. It addresses D-Wave's platforms as well. And in order to actually efficiently gauge whether I'm doing the things correctly or not, I actually collaborated with D-Wave. They actually looked over the material that I have written in the book about them, and I got their okay to go ahead before publication. So I'm very grateful to them for that. So yeah, I mean, that's what triggered my my interest, that I wanted to do something that would give the readers an option, an entry point to all different major platforms, and hopefully an idea of which algorithm works best on what kind of platforms and how to get around them.
You mentioned that some algorithms work better on some machines, but there's even a bigger question. Is quantum machine learning useful today, or when do you expect it to be useful in a production environment?
That's a very good question. My response to that would be quantum machine learning in certain cases is definitely useful today. So one of them is drug discovery and molecular modeling. So this is something that is being researched on. It is a current topic, but this is something that has also worked. I'll give you an example on that. My apologies. Penn State University, under Dr. Ghosh, started to use quantum computing and machine learning in order to investigate vaccine modeling for the COVID virus. So that's one example of it. The other example of where quantum machine learning is being researched upon and actually being used is in the financial sector. So for example, in financial risk analysis, in financial portfolio optimization, derivative pricing. So there are several published works from Goldman Sachs, from Chicago Quantum, who are actually looking into quantum version of finance. The reason the quantum angle is being investigated is because of the plethora of choices that you get. You get all sorts of probabilistic choices in a quantum computing and machine learning environment that you normally struggle to get in a binary environment. So it is being used, and hopefully as the usage goes up, we'll learn more and more about how to optimize different applications with different algorithms on different platforms. And we will improve, as we did on our own, standard classical computers. When I was a kid, a classical computer was a big thing sitting on my desk. Now it's in my pocket, literally. So more we use, more we should learn.
Now, when you mention running on different computers, I'm guessing you mean different types of architecture. So, PsiQuantum versus Honeywell, and not so much Rigetti versus IBM, both sort of gate-based computers. Is that correct?
That is correct. Absolutely. It's different architectures. Then there are other aspects of both machine learning, computing, and communication, which is, let's say we have two different computers, quantum computers. These quantum computers could be two IBMs, could be one IBM and one Rigetti, could be one D wave and one Rigetti, whatever. How do these two computers communicate between each other? That has not been done. And this is a huge area of research where I'm involved, and a lot of other research outfits are involved, because this brings into question, how do you get information from a qubit level up to a level where you can communicate with another quantum platform, especially if the level is optics. Right now, that's all we know. We think, okay, optics should be the communication media, but you have a superconducting quantum platform at minus 273 degrees centigrades, close to 0 degree Kelvin. And then from there, you need to get the information up to an optical level and then communicate with each other. So there are research bodies, for example, one in University of Berkeley, who is working on this for a long time. It's called flying qubits. So basically, you fly the qubits from one energy level to another to transport them over the communication barrier. So yes, the architectural differences they play a major factor, as do basic science and application we are considering.
Now, if I work at a commercial company and I want to do chemical research or portfolio optimization, and I want to try machine learning, do I have to a priori decide what hardware architecture will I run it on? How do I know if this is going to be best on D-Wave or IBM or something else?
Right now, there are two ways. The way number one is kind of an approximate way. So you kind of guess, okay, I'm going to run a max cut algorithm. Is this going to work better on a D-Wave or an IBM? And then you try it out. So that's one way. The other way is blind trial and error way. Okay. Now, to resolve these differences in various platforms and this applicability of, or rather efficiency of, different algorithms on different platforms, there could be, and I think the works are underway via various startups and if not other quantum computing companies, where people are thinking about building up stacks on top of the physical quantum computing and communication level, where we have some sort of an orchestration level, which will make the physical layer underneath invisible, so to speak. In other words, the user would not care if an algorithm, if the platform they are programming on is an IBM or a D-Wave or whatever else, as long as they know what they want, which algorithm they're which algorithm they're going for, my apologies, they program it, and then the underlying software stack picks the best platform for them and allows them to program on it. So this is something that people are working on, under research, and possibly there are startups, one or two around, who may even have the first generation solutions for these. So this could be another way of actually addressing this disparity in architecture and underlying layer.
If we look at where we are today with quantum machine learning and fast forward and say, okay, what does it need? What needs to happen for it to be a truly useful tool beyond one or two specific use cases? Then one thing that you mentioned is that abstraction layer, or the ability, just like Classiq does, to go from a functional high-level model into a quantum circuit that so you don't have to decide ahead of time which hardware you're using. The second thing is obviously an improvement in the noise characteristics and the number of qubits, so you could run larger models and run longer algorithms. Is there something else? Is there a third or fourth thing that you envision that's missing for quantum machine learning to become mainstream?
I think Well, I won't say it's missing. I mean, it's probably under research. Not probably, it's definitely under research right now, and people are working on it. And that's basically coherence. And you mentioned errors, and you also mentioned disparities and abstraction layers. So besides this, there is, not everything is going to be optimized or usefully optimized by quantum computing or machine learning. For example, if you're using PowerPoint across networks, there's no point in running it on a quantum channel because PowerPoint will work, much better possibly on a classical network. So there would be, going forward, and from a futuristic point of view, there will be specific applications that machine learning will be useful for. And to address those, to go back to your questions, to address those, what we'll need is refinement in basic qubit processing. Right now, the way physical qubits are actually created, that is not perfect. So there needs to be optimization in that process itself. And then, obviously, we'll need more qubits. Right now, you get about 53 qubits on a real quantum computer. And most of the algorithms that are being are first tested on simulators. And then, if you don't need enough qubits, they're run on actual platforms. So we actually need that. We need that physical layer. We need the abstraction layer. And then the other option and challenge is obviously scalability. So the problem needs to be meaningful. And in terms of a meaningful problem, we need to scale it. I'll give you an example. So you may have seen on the internet that there was a traffic optimization study done in Southeast Asia. So the city they picked has humongous traffic congestion. And then they did a machine learning study based on some constraints such as distance and fuel, people's work destination, which way do you get, rush hour traffic, etc., etc. So, and they had an optimized model, which is mathematically optimized. But if you look at that graph, you see that the machine learning algorithm is sending drivers, my apologies, from one point to another around the city, not through one of the quicker paths possible. Now, they are doing it based on a constraint of time. But how many people do you know who, if they can drive from destination A to B in 5 kilometers, is going to take a 20-kilometer roundabout way to save 10 minutes? Not many. So we need to find out how practical it is to run these things. Will it actually be a practical solution to the problem in hand? And how to scale these queries. In a rush hour platform, in a financial environment, for example, you may get hundreds of thousands of queries. Now, are all those queries going to be efficiently serviced by quantum machine learning, or would it be 50-50, some classical, some quantum? So these are areas where we need more clarity. And more importantly, once we have the clarity, we need more real-time decision making. So there should be a layer, be that AI governed, be that ML governed, which would say, okay, this is best served by quantum, this is best served by classical, go your different ways and do your magic. So that's my take on it.
As we get closer to the end of our conversation today, we spoke a lot about quantum machine learning, but obviously there are other areas in quantum computing, quantum key distribution, and others. Is there anything in particular that drew you to focus on quantum machine learning?
Yes, fundamentally, quantum computing is of deep interest. Attached to quantum computing is the great question today of security. That is also of deep interest. The other thing of deep interest is quantum error correction. there are aspects of quantum security and quantum error correction, both which can be addressed by quantum machine learning, reinforcement learning, or supervised learning or unsupervised learning, some such algorithm. And there are research and studies that's going on that. So my interest is tied to specifically these domains. And that's where machine learning became interesting, because it can actually solve some serious unanswered questions in quantum computing today, as it exists today.
So, Shantanu, where can people get in touch with you to learn more about your work?
Thank you very much. I'm on LinkedIn. If they do a search with my name and Cisco after that, I should pop up. And there, or quantum after that, I should pop up. Feel free to reach out to me via LinkedIn, and I'm usually quite proactive in answering. I'll be very happy and glad to respond to anybody who has any questions at all. Thank you.
That's excellent. I enjoyed very much speaking with you. Thanks so much for joining me today.
Thank you very much. Likewise, it has been great talking to you. It's been a pleasure and an honor. Thanks for having me.